So recall that a regression line is used to predict a variable, y, from one or more independent variables, x. Multiple linear regression, as we've noted previously, is a regression formula that's a single response variable, or dependent variable, estimated by more than one predictor variables, or independent variables. These are labeled as x1, x2, all the way up to xn, however many you have. The concepts are generally the same as our simple linear regression, and the interpretations shown in the next slide work for both single and multiple regression. So we're going to focus on a few key concepts. Multiple linear regression formula itself, how we interpret the coefficients, and the overall performance of multiple regression formula in terms of explanation of variance. So in our example from the previous module, we obtained a regression equation that looks like the following. Predicted refund requests equals 1.798, which is our intercept, plus 1.176 times complaints. Our main focus in interpreting the equation is that for every increased complaint, we have the refund requests increasing by 1.176. Thus, if you have 10 additional complaints, you will have 11.76 additional refund requests. Now, don't worry too much about interpreting the intercept, but in this case, one can interpret it as the value when the predictor is 0. In other words, when the number of complaints is 0, we have about 1.79 refund requests. The intercept isn't always interpretable, but it's not a big issue because most of the time we're really concerned with the coefficients of the variables. To the right, you can see what we've got highlighted in green. The coefficients are in the bottom section, where we have our intercept of 1.79 and our complaints of 1.17. So here's a new example in the data set, only with an additional column. We're going to add in the sales. In this example, we've added a column for sales, and we're trying to predict refund requests from both sales and complaints. Therefore, our general model now looks like this. And we've now substituted with the traditional statistical letters of beta for each one of the coefficients in the intercept. So beta 0 is our intercept, beta 1 is the coefficient for the first variable, beta 2 is the coefficient for the second variable, and epsilon is our variable for the residuals. From the data set on the previous slide, we obtain a new regression formula using the analysis tool in Excel. And we end up with the predicted refund requests equaling negative 20.86 plus 0.974 complaints plus 0.022 times sales. So interpreting the coefficients, we would say that for every unit increase in complaints, the number of refunds increases by 0.974. Or more likely, every 10 complaints yields approximately 9 refund requests. Additionally, as sales increase, so too do the number of refunds. For every unit increase in sales, the number of refunds increases by 0.022. Or more practically, that every $1,000 increase in sales, the number of refund increases by 22. Errors are the same in multiple regression. They are the actuals minus the predicted value. The formula for the standard error of the estimate is slightly different, because now we need to take into account the added variables in the equation. So the standard error of the estimate is again the standard deviation of the residuals. This is equal to the square root of the sum of the errors squared divided by n minus k minus 1. Now the formula is essentially the same as the one for linear regression. In this case, k is the number of variables we have in our model. Therefore, if we take n, assume it's 30, and subtract 2 for the number of variables in our model, and then we subtract 1, we have 27 as the denominator of the fraction. Now remember, in simple regression, we had one variable, which would make the value of the denominator n minus 1 equals 28, which is the same thing as n minus 2 that we had on our simple linear regression slides. We interpret this number again as the expected error for our prediction using the model. Just as with simple linear regression, we use the R statistic to explain the variance. However, with multiple regression, we've added more variables. And as you add more variables, R squared value will always increase. And this is a critical point. If you continue to add variables, your R squared will always increase because you're adding more ways to explain the variance, so it will never decrease. It can never get worse. But this poses a problem, because an analyst may keep adding variables believing that the model's getting better in explaining the variance when in fact that's not happening. So we have a different statistic which will be the one you should use. It's called the adjusted R squared. The adjusted R squared penalizes the model for increasing the number of variables, and therefore it's a better metric to use. Our entire goal is to create as parsimonious model as possible, A parsimonious model is one in which the model uses the least number of explanatory variables to explain as much of the variance as possible. So the interpretation is exactly the same, whereby an adjusted R-squared of 0.89 means that 89% of the variance in y is explained by the regression model. The formula on the right shows that it's R-squared minus 1 minus R-squared times P over n minus P minus 1, where P is the number of explanatory variables in the model, and n is the number of observations. So it's a very similar calculation, and it's using the specific components, but it's penalizing you for using extra variables. So consider a model with 5 variables and adjusted R-squared of 0.87. You may have another model with 4 variables and an adjusted R-squared of 0.866. Which model should you choose? Well, the analyst should generally choose the simplest model with the highest explanatory power, and we'd probably choose the one with 4 variables. Now, there are some other methods that we have at our disposal that will tell us which one we should choose. But generally, if you're adding 1 to 2% on your R-squared, it's probably not enough to warrant the added extra variable.